I'm here with Dr. Romano to do a video on quantum numbers.
Hi, I'm Dr. Romano. I'm professor of organic chemistry here at Romano Scientific and the author and the creator of the DAT Destroyer and Orgoman books. I want to go over a few problems that you're likely to see on the DAT involving quantum numbers. We only need to do very basic type of questions on this, so if you understand this type of question, you're good to go for the DAT. So come around and let's have a look at what I got for you. I'm going to do 5 questions, all DAT style. The first question says, how many electrons in an atom can have the quantum numbers of n equals 4, L equals 2? Well, we all remembered, if this is the nucleus, this represents the first energy level, the first principal energy level. Then we have n equals 2, then n equals 3, and n equals 4. Each principal energy level is divided into a sublevel. So this would contain an S sublevel, this an S and a P, this an SPD, an SPD, and an F. Now we should remember the S sublevel can hold 2 electrons max, where the P can hold up to 6. So again, following this through, and then the D can hold 10. And again, this is 2, 6, 10, and F is 14. So the maximum number of electrons in the first energy level would be 2. Here, 6 and 2 would be 8. And then 6 and 2 is 8. And we add 10, we get 18. 2, 8, 18. And then when we add these up, we have 32 electrons. You should know that. Now, if n is 4, L is 2. The L quantum number is called the azimuthal number, and it's going to describe the shape of the orbital. If L is equal to 0, we are describing an S-shaped orbital. If L is 1, P, if L is 2, D, and if L is 3, F. So n equals 4 and L is 2 is describing the sublevel of 4D. Well, in any D, it doesn't have to be 4D, it could have been 3D, 4D, 5D, etc. The D's start at the third principal quantum level. Any D can hold up to 10 electrons. So there would be 10 electrons that can have these 2 quantum numbers. Part B. If n is equal to 2, how many orbitals are possible? Well, if we go back and draw our little picture, n equals 1, there's an S, and n equals 2, there's an S and a P. So if the S sublevel has 1 orbital, the P sublevel, you should remember, has 3 orbitals. And that would be Px, Py, and Pz, which gives you a total of 4 total orbitals. Don't forget, the D sublevel has 5 orbitals, meaning these are the areas of space, and the F sublevel has 7 orbitals. All right. 14,7 nitrogen has how many unpaired electrons? Well, we know there's 7 electrons, so if we write the configuration out, we have 1s2, 2s2, 2p3. And as you can see, all these are filled up. These are not. There's 3, this is the P sublevel, so there's 3 P orbitals, 1 electron in each, and therefore you would get 3 unpaired electrons. Don't forget, anything with unpaired electrons means that it's going to be paramagnetic. Letter D. Xenon 4F14, notice the F can hold 14 electrons. Any orbital can hold 2 electrons maximum. And as you can see, this is 2. Since there's 3 P's, we can hold 6. Since there's 5 D orbitals, we can hold 2 in each is 10. And there was 7 F orbitals, 2 in each is 14. Now, this configuration of xenon 4F14, 5D7, 6S2 is blank. All you're going to do is you look up on the periodic table, we have 54 for xenon. That's the atomic number, which is the number of protons, which is also equal to the electrons. You add 54 plus 14 plus 7 plus 2. Now, when you add them all up, you get 77, and that would be iridium. And don't forget, iridium is a transition metal. All right, let's do one final problem. And this would take care of 5 questions on the DAT. What is the electron configuration of titanium plus 2? First of all, be very careful of what I call the sucker question. Whenever they give you a transition metal ion, always draw the ground state first. So we're going to look up 48 on the periodic table, 22, and write the configuration. So it's 1s2, 2s2, 2p6, 3s2, 3p6. Now after the 3p, you got to just remember comes the 4s. So it's 4s2, 3d2. Now, titanium plus plus means you lost 2 electrons. You go to the valence shell. The valence shell is the one with the biggest number. And as you can see, this is where we're going to remove the 2 from. So with this removed, you get 1s2, 2s2, 2p6, 3s2, 3p6, 3d2. Or if you just clean all this up, this represents 2, 4, 10, 12, 18, which is the configuration of argon. So we could also write this as argon core 3d2. Notice there's 2 unpaired electrons, and it would also be paramagnetic. I hope this helps. This gives you a good idea of the type of questions they're going to ask in the DAT. If you got any questions, you can visit my study group, and we can discuss questions like this further. The 2018 Destroyer and beyond, I always try to make up-to-date questions. So make sure you're using the newest edition of our book. Okay, good day to you. Bye-bye.